addition of graphs, sometimes called superpositioning. Physics, I think they call it that. Do they mention the superpositioning of graphs? Okay, so it's basically just adding two functions together. So really all we do is we draw the two original graphs and then physically add their y values, known as ordinates, together. So let's do a very simple one. Y equals x squared plus x. So there's y equals x squared, there's y equals x. I just want to add these two curves together. So the x-intercepts and the y-intercepts, they're always interesting ones. I know when I add 0 with 0, I get 0, so that's clearly an x-intercept. The other time we'd get an x-intercept is where the above equals the below in the y value, because one would be, say, positive 3, the other would be negative 3. That's just a matter, I guess, of sliding your ruler along and then going, oh, look, they're the same distance above and below. So I know that's where the x-intercept is. So on my one, it ends up about there, I think. Somewhere about there it'll have an x-intercept. No others, because on the right-hand side they're completely above. Now, how do you find? As many lines as you need to do it. So basically you draw perpendicular lines. Well, I say draw. Again, it might just mean you're getting your ruler and putting it there and reading off the measurement. But, all right, the point of intersection is always a good one, because that's going to have the same y value. Add them together, you'll just get twice whatever that amount is. And then, as I say, I've gone a bit crazy there. Well, just a few vertical lines. But at each of those, I'm just going to add. And in this case, it'll be a negative, whatever that measurement is. Let's say it's, I don't know, on my graph it might be 5 centimetres. And so I'll mark off 5 centimetres below this one. And so on, and so on, and so on. And I just keep doing that until I've got an idea of the shape. And we can see it's sort of emerging there. And then it's just like playing dot to dot, except with a smooth curve. Not like when you were back in kindergarten and you went... Ooh, then we get our parabola. How many points? Again, just as many as you need until you've got the shape and you think, yep, I know what this thing's going to look like. X plus 1 on x. There's y equals x. There's 1 on x. Okay? X-intercepts. This one's not going to have any. Right? So I'll add, before I do that, let me explain. It's not going to have any because in y equals 1 on x, we've got a problem with the domain. Now when I add the two curves together, it can't all of a sudden magically exist this point. I still can't substitute x into x plus 1 on x. So it will still have an asymptote or maybe a point discontinuity, but something is going to be happening there. So I'll just go to adding. So the point of intersection, okay, double that one, I'll double the other one, and I'll just pick points. And what's actually happening here is these points are getting closer and closer to y equals x, because it's sort of like saying the original graph was getting closer and closer to the line y equals 0, because the original graph was 0 plus 1 on x, and the hyperbola was getting closer and closer to it. Well, now it's x plus 1 on x, so it's getting closer and closer to y equals x. So there's x plus 1 on x. Okay, keep in mind, as I just mentioned, any discontinuities will remain. They're not going to change. Can't magically exist. Oh, this is interesting. So if I add these two graphs together, x plus 1 on x plus 1 minus 1 on x, you would think you're going to draw the line y equals x plus 1. You do, sort of. A bit like what I did on the board over there. X still can't equal 0. See, we're not drawing the line y equals x plus 1. We're drawing function x plus g of x. They have domain issues. X can't equal 0. So when I draw in y equals x plus 1, I just have to put a point discontinuity at x equals 0, because that can't exist. Again, the difference between saying drawing y equals x plus 1 and drawing function x plus g of x are the two different graphs. They look very, very similar, but they are actually different graphs. X-intercepts, that's what I was saying about when above and below match, that's when it's going to become 0. So slide your ruler along to estimate, things like that. Symmetry. like functions retain symmetry. You'll notice in this graph, y equals x and y equals 1 on x are both odd functions. They both have that rotational symmetry. And then when we drew our new shape, it still had rotational symmetry. It kept its symmetry. An odd function plus an odd function will remain an odd function. An even function plus an even function will remain an even function. These ones are always interesting. Absolute value curves, when we add them together. I like to deal with their critical points. The critical points here is when the absolute value is going to be equal to 0, because that's when it will change from minus to plus. So -3 is a key point. If x is less than -3, then x plus 3 will be negative. So the absolute value of x plus 3 will actually be minus x plus 3. The definition of absolute value. Either it's plus this or minus this. Now 1 minus x, if I put a number in that's less than -3, that's going to be positive. So it will stay as 1 minus x. So I know that for values of x less than -3, I'm going to draw the line y equals minus 2x minus 2. Okay. 1 is the other key point here, because that's when 1 minus x will equal 0. So what if it's in between those 2 points? Okay. Substitute into the first one, we're going to have a positive number. So it'll stay as x plus 3. Sub it into the second one, it'll be a positive number as well. Add them together. Oh, we're just going to get the horizontal line, y equals 4, in between those 2 points. Now let's investigate over a greater than or equal to 1. The first one, well, that'll stay positive. The second one, well, that'll be negative, the second one now. So it'll be minus 1 minus x. Add those together, 2x plus 2. So let's draw that in. It'll stop at -3, and the y value at that point, coincidentally, is 4. I suppose that's not that amazing, consider what the middle section's doing. So I just draw that piece. In the middle, it's the horizontal line. And then on the right-hand side, it's y equals 2x plus 2. And there's our graph. Y equals the absolute value of x plus 3 plus 1, the absolute value of 1 minus x. So deal with where the boundaries change, if you like, where it changes from plus to minus. Now, this was adding, and I did say it was adding and subtracting. I think of it all as adding, because if I want to draw function x minus g of x, then instead of graphing function x and g of x, I graph function x and minus g of x, and I'm still just adding 2 graphs together then. Graph of y equals x plus g of x, where g of x is bounded. So there's something happening with the range. It's bounded. Remember that term we had, what was that, back in the first topic we looked at, whether something was bounded or unbounded? All right, if the graph of y equals g of x is bounded, which our sine curve is, it's bounded at 1 and minus 1. Then when I add them together, x plus g of x will be bounded by x plus that number and x plus the other number. So this one should be bounded between x, what was it again, plus 1, x plus 1 and x minus 1. Now notice it's x minus sine x I'm drawing. So that's, I haven't drawn the sine curve in, I've drawn minus sine curve. It becomes an adding one again. Okay, drawing some key points there. X-intercepts are great because if you add 0 to the other curve, you're always going to get 0. So they're the 3 points I've drawn in. And when is it above and below the same? Sorry, the turning points is what I've looked at there. So the turning points are always good ones. Add the turning point and we get those 2 points. And there's our new curve. Unfortunately, the scale of it, you don't see the full effect of it, but what you've got is a curve winding along y equals x. It's not symmetric, you'll notice, because it's now at an angle. So whereas the original sine curve was lovely and symmetric as it went along, the humps are not symmetric. Multiplying. The 2 basic ones. So we're going to draw xe to x all the way down there. So there's y equals x, there's y equals e to the x. We're going to multiply these 2 curves together. Find the x-intercepts. That's where the new function will change sign. Well, if you're multiplying two curves together, one of them has to be 0 to get an answer of 0. So the x-intercepts will be the x-intercepts of the two curves. Well, there's only one. It's down there at y equals x. I want to see, is it going to be positive or negative? So I just look at the original curves. So over here, e equals x is positive, y equals x is negative. Positive times negative is negative. So I know the curve will be down there somewhere. I've got to end up with negative numbers. When I go on the right-hand side of that x-intercept, everything's positive in both curves. Positive times positive will give me a positive. So I know I'm in that section there. Y-intercept, if we can find it, it's always good. Well, I've already got it there. It's 0 in this case. 1 again becomes a key point, because if you multiply by 1, then you must be on the other curve at that same point. So when y equals x is 1, I know it'll be at the point on y equals x. So let's plot that in. There's where y equals x is 1. Therefore, I must be there. That was that quick. So that's where x equals 1. I'm saying I'm 1 times the y value on e to the x, so therefore the y value must be the point on e to the x. 1 times everything's 1. I can do the same with negative 1. If there's negative 1, then when I multiply the other one, but remember it's become negative, so it's a reflection in this case of where it is. So I know I'm going through those points. If either function approaches 0 or infinity, so will the new one. Hang on, this one's doing both. That's interesting, we'll come back to that. But over here, e to the x is going towards infinity, y equals x is going to infinity. So this new curve is going to go to infinity. E to the x is going towards 0, x is going towards negative infinity. 0 times infinity? This is where an idea called dominance comes in. Which of those two functions will dominate? And the one that dominates is the one that gets steepest or shallowest the quickest. So have a look at the two graphs. Which one is getting steeper or shallower the quickest? That one will dominate. So whatever it's doing, the new graph will do. So our new graph will approach 0. And get a little bit dodgy with my bump there. So we'll get something like that. It'll go through those points. It's going up to infinity, coming down and to 0 on the left-hand side. Keep in mind. Again, discontinuities can't magically reappear. Symmetry. When you're multiplying, you'll get some form of symmetry. Right? An odd function times an odd function will always give you what? If you're not sure, go back to the simplest one you can think of. What's the simplest odd function you can think of? Okay? What's x cubed times x cubed? 6. Even. Odd times odd will give you even. Odd times even will give you odd. And even times even. So if it's the same type, they'll multiply together to give even. If they're different types, they'll multiply together to give odd. All right. I'm going to multiply x squared with x plus 1, x minus 1 cubed. I'm identifying the x-intercepts. Okay? When I multiply them, they will remain as x-intercepts. But that tells me the boundaries where it will change from positive to negative. So on the starting at the left, I've got positive times negative, while I can't see the purple one, negative. Positive times negative is positive. In between these two, positive times negative, negative. Positive times negative. Positive times positive. We know that's where it goes. You remember back earlier when we looked at curve sketching, we said the x-intercepts will act like the powers. So we know it's going to turn like a parabola at 0. We know at 1 it'll act like a cubic. There it is. A bit hard to see under the purple. Let's get rid of the purple. So there's the green curve, our new one. Now it looks like, because of the scale, it looks like I've just gone flat. But actually it is actually coming down and going back up there. But the scale's so small that you can't tell that there. All right, y equals the square of a function. Single roots will become double roots because you're now squaring it. Here's my random curve again. So my x-intercepts, they stay. This, where it cut like a linear function, it'll now turn like a parabola. Same with the other two. They were single roots, they will become double roots. Those stationary points will stay as stationary points. The y value might change, but at that x value. So if I square it, well, square a number bigger than 1, it's going to go up there somewhere. A number smaller than 1, but of course this is negative, so it becomes positive. Discontinuities remain. Horizontal and oblique asymptotes will change. Basically square them. We're squaring everything. Horizontal asymptote, there it is. If the original function is bigger than 1, then the new function will be bigger than the original function. Square a number bigger than 1, you get something big. So the new curve will be above the old curve. If it's less than 1, the new curve will be below the old curve. Let's try that. So there's 1. That's important, so I know when to go above, when to go below. So here, when I draw this, it's below, so it'll go above. Here, it'll go below. Let's just draw it in so we can see. Ooh, look at that. Okay. So it's under, it cuts at 1, goes above. Over here, well, a bit hard to tell with the negatives, but when we get to the positives, it's under because it's below 1, but then it's above when it gets above 1, and so on, and so on. And eventually, lovely little graph. Division is the same as multiplication. It's just that you're multiplying by the reciprocal. So x-intercepts will now become vertical asymptotes, maybe point discontinuities. We'll do this one. We've just got 4 lines there. I've got x-intercepts at -1 and +2. I will have vertical asymptotes at -2 and +1. Let's work out the regions. Negative times negative times negative times negative, it's positive. Positive times negative times negative times negative, and so on and so on and so on. 1 stays at 1. Now, some sort of investigation will be required. Horizontal and oblique asymptotes. That idea I talked about, dominance when you're multiplying things together. In our case, I can do back to that idea of polynomial division we saw before. Okay, aha, horizontal asymptote at 1 when I do my division. So we've got horizontal asymptote at 1, let's put it in. That's what that curve ends up being like when we go bending towards the asymptote, passing through those points, and so on. Sine x divided by x. There's y equals x, there's y equals sine x. All the x-intercepts will become x-intercepts, because sine x is on the top, except for x equals 0. It's on the bottom. It's either going to be a vertical asymptote or a point discontinuity. Now we don't know this yet, but it turns out that the limit as sine x on x approaches 0 is 1. So it'll actually go to a point discontinuity of 1 this curve. So I'll just put that in there. And that's just working out the regions. Positive times negative, negative times negative, so on and so on. And there's where we get the sine curve. What has happened is, when you think about it, we're dividing by bigger and bigger numbers. So as it's winding along the x-axis, it's getting smaller and smaller and smaller. But it starts at 1. It ends up being an even function. Sine x is an odd function. X is an odd function. So same type of function, it'll become even. There it is. A little bit bumpy there, but okay. So symmetry, that's what I was saying before. Odd times odd will be even. Even times even will be even. Oops, odd times even will be odd, of course.